One of Einstein's most famous thought experiments has to do with a train. Einstein thought, what if there is an observer in the middle of a train and another observer by the tracks? And let's say that at the exact moment the observer on the train passes the observer by the tracks, the observer by the track sees lightning strike both ends of the train at once. What would the observer on the train see? Einstein concluded that the observer on the train would not see the lightning strikes at the same time, but would see one before the other. You can find many explanations of this thought experiment, but everyone I've seen gets it wrong. They all violate the basic tenets of special relativity. So I decided to see what did Einstein himself say. I got a copy of the English translation of his book, turned to the page on simultaneity, and Einstein gives the same wrong explanation everyone else does. How could this happen? There's nothing wrong with Einstein's theory, but his explanation violates the tenets of special relativity. This is like Eratosthenes saying that the Earth is flat, or like Copernicus saying that the Earth is the center of the universe. So let's take a look at the thought experiment and see what went wrong. Let's set the scene. We have a train with an observer in the middle. We also have an observer standing by the tracks outside the train. Now, lightning strikes both ends of the train at exactly the same time. Of course, the observers haven't seen anything yet because the light from the lightning has yet to travel to where the observers are observing from. So the light from the lightning is speeding toward the observers at the speed of light, which is 299,792.458 kilometers per second, and is represented by the letter C. The blue line below the train represents the light that will be seen by the observer by the track, and the blue line above the train represents the light that will be seen by the observer on the train. And finally the light reaches the observers, and that's when they see the lightning strikes. The train is a very long train. The distance from either end of the train to the middle, where we have our observers, is 299,792.458 kilometers, or the distance light travels in 1 second. So our observers see the lightning strikes 1 second after the actual strikes. This is exactly what happens if neither observer is moving. The lightning strikes the ends of the train, the light travels to the observers, and 1 second later the observers see the lightning strikes. Now let's see what happens if the train is moving. Let's have the train moving from right to left at half the speed of light. Now, just as the observer on the train is passing the observer by the tracks, lightning strikes both ends of the train. As the light is traveling toward the observers on the train is moving toward the light that is coming at him from the left strike. Since they are moving toward each other, the observer on the train meets the light coming from the left strike after only 1/2 second. The light still has another 1/2 second to go before it reaches the observer by the track. Therefore, the observer by the track sees the two lightning strikes 1/2 second after the observer on the train has seen the left strike, and the observer by the track sees both strikes simultaneously. The observer on the train is moving away from the light coming from the right strike. That light won't catch up with him for yet another 1/2 second. So the observer by the track sees the lightning strikes simultaneously, but the observer on the train sees the two lightning strikes at different times. This is the explanation in the English translation of Einstein's book that is repeated time and again, and it makes perfect sense, except that it violates the very principles of special relativity. The first principle it violates is that all observations are made from a stationary frame of reference. An observer's observations cannot depend on whether or not the observer is moving. If this were happening with two spaceships, with no track, rocks, trees, or cactus whizzing by, the observer on one spaceship cannot tell if he is moving, or if the other observer is moving, or if they are both moving. And when it comes to observing the behavior of light, your observations cannot change due to your motion. Neither observer can see any difference when he is in motion compared to when he is not in motion. In the scenario we just saw, if the train is moving, the observer on the train sees the events differently than if the train is not moving. This cannot happen under the mandates of special relativity. The second principle of special relativity this scenario violates is that the speed of light cannot change because of your motion. The speed of light to every observer is always 299,792.458 kilometers per second, regardless of the observer's motion or the motion of the object emitting the light. In the scenario we just saw, we have the light from the left lightning bolt traveling to the right at the speed of light. At the same time, the observer on the train is traveling toward the light at 1/2 the speed of light. Therefore, they have a closing speed of 1.5 times the speed of light. This is fine if we have, say, two fighter jets closing on each other. Let's say the jet on the left is going at 1,000 kilometers per hour and the jet on the right is going toward it at 500 kilometers per hour. They have a closing speed of 1,500 kilometers per hour. No problem. But this cannot happen when light is involved. Under no circumstances can the speed of light be exceeded. Let's take another look at one of our fighter jets. Let's say it is an impossibly fast fighter jet and is flying at 1/2 the speed of light. Now let's say the pilot turns on his landing light. If the pilot could see the photons that make up the light beam, he would see them streaming away ahead of him at the speed of light. Now let's say that there's an observer on the ground watching the jet approach. He sees the jet approaching at 1/2 the speed of light. If he could see the photons that make up the light beam, how fast would they appear to be approaching? The jet is approaching at 1/2 the speed of light. The photons are streaming away from the jet at the speed of light. The photons are getting a speed boost from the jet, so naturally they are streaming toward our observer at 1.5 times the speed of light. Except they're not. The speed of light is the speed of light. No observer can measure light moving at any other speed, no slower, no faster. Both observers would see the photons, if they could see them, moving at the speed of light. So let's say the pilot turned on his light just as he was 299,792.458 kilometers from the observer on the ground. At that distance, it will take exactly 1 second for the photons to reach the ground observer from the jet. Now let's say our ground observer puts on his light speed running shoes and takes off away from the jet at 1/2 the speed of light. Can he outrun the photons long enough to delay the time they will reach him? Not a chance. His fate is sealed. Once the photons start their journey, nothing the observer does can delay or hasten the time the photons reach him. If he takes off running, his frame of reference remains stationary and the photons just keep coming at the speed of light. It's like that bad dream where you try to run away from the monsters and try as you might, you just can't run away. The same thing if he tries to run toward the photons. He can't intercept the photons earlier. All he can do is wait for them to arrive in their due time. As bizarre as this may seem, it has been proven time and again. It is a fact of physics and the world of special relativity. The third and fourth principles of special relativity the scenario violates are length contraction and time dilation. When an object moves relative to your stationary frame of reference, it becomes shorter in the direction of motion. At the same time, time goes slower for that object. So, when your friend runs by, not only is he thinner, but time goes by slower for him as well. At least as you see it. He sees time going at his normal speed, but you see time going slower for him. So what would really happen to our rail-bound observers? Let's take a look. First of all, the train is moving, so it's shorter as viewed by the stationary observer. Let's start the train moving, and now we see our first problem. The train is shorter, so the lightning bolts missed it. So what can we do? Our thought experiment requires that both bolts strike each of the ends of the train simultaneously as the observers pass each other. That worked fine when everything was stationary, but now the bolts missed their targets. The only thing we can do is cancel our lightning bolts and order new ones that are closer together and start over. So let's push the bolts closer together and restart the experiment. Now here comes the train. When the observer on the train passes the observer by the track, the lightning strikes. Now the train is shorter, so it takes only 0.0866 seconds for the light to reach the observer by the track instead of 1 second. The stationary observer still sees the strikes simultaneously. Now let's see what the observer on the train sees. The observer on the train must see himself and the train as stationary. Therefore, the train is not length contracted, so we can stretch it back to its normal length. Now let's start everything in motion. Here comes the observer by the track, and just as he passes the observer on the train, the lightning bolts strike, and look what happened. We had to push the lightning bolts closer together so they would hit the ends of the length contracted train. Now they are too close together to hit the ends of the normal length train. It's worse than that. Now the observer on the train sees everything outside the train as moving at 1/2 the speed of light. So everything outside the train is length contracted. Therefore, not only does he see the observer by the track as considerably skinnier than when he wasn't moving, but the points in space where the lightning bolts hit are even closer together. So what can we do? Here's where time dilation comes to the rescue. From the frame of reference of the observer on the train, time is going slower for everything around him. In addition, the points in space along the track are at different times. This causes time and space to line up differently for him than it does for the observer by the track. Once we adjust for time dilation, the point in space where the left lightning bolt strikes lines up with the front of the train just as it strikes. But the point in space where the right lightning bolt will strike has yet to reach the rear of the train. That's okay. Due to time dilation, the right bolt strikes just as it reaches the rear of the train. From the frame of reference of the observer on the train, the bolts are too close together to strike the ends of the train at once. However, time dilation causes the lightning bolts to strike at different times, just when they pass the appropriate ends of the train. This may seem as bizarre as the unchanging speed of light, but like the unchanging speed of light, length contraction and time dilation have been observed and proven to be facts of physics and special relativity. If you want to understand the math behind this, Dr. Don Lincoln explains the math in an excellent video linked in the description below. So, Einstein got it right. The observer on the train will see the lightning strike the front of the train first, but not the way it is explained in the English translation of his book. The book says the observer on the train will see the lightning strike the front of the train first because he intercepts the light coming from the bolt before it reaches the observer by the track. However, if we properly apply special relativity, we see that the observer on the train sees lightning strike the front of the train first because, from his frame of reference, it actually does strike the front of the train first. So what happened? Did Einstein explain it wrong? Did his editor change what he said? Did the English translator make a change, or did his editor? We don't know, but now you know how the experiment really works.